In the thermochemical calculations activity, we are working with transfer of energy. We are working with the transfer of energy in the form of heat, and that's due to a temperature difference between the surroundings and the system. The quantity of heat transferred is given by the equation Q equals Sm delta T, where Q is the energy gained or lost as heat in units of joules. S is the heat capacity of the matter in units of joules per gram degrees Celsius. M is the amount of matter in grams, the mass. And delta T is the final temperature minus the initial temperature in units of degrees Celsius. It could actually be in Kelvin too. And it transfers from the surroundings to the system or the system to the surroundings, so that the amount of heat transferred from one to the other is equal, and we have the negative sign when we're equating Q of the system to Q of the surroundings, because that implies a transfer from one to the other. One's energy goes up as the other one's energy goes down. The amount of energy, of course, is equal. Now, we can think of heat in terms of this symbol Q. We can also think of it in terms of delta H, the enthalpy change involved in the process, which for us chemists is usually a reaction. Okay, so let's look at this example here. Sample problem. Calculate the amount of energy as heat associated with raising the temperature of 250.0 grams of water from 24.3 degrees Celsius to 100 degrees Celsius. We're told the heat capacity of the water is 4.184 joules per gram degrees Celsius. And we have our equation, Q is Sm delta T. Now, this heat energy is coming from the surroundings to the system being the water. So we know it takes energy to heat water from a low temperature to a high temperature. In our case, we're basically taking it from room temperature and boiling it. And anyway, so heat's going into the system. We expect it to be positive. So we use the Q is Ms delta T equation. We put the value of S in, 4.184 joules per gram degrees Celsius, multiply by the mass, 250 grams, and we multiply by the temperature change. Final minus initial, 100.0 minus 24.3, and we then, after we have done the multiplication and canceled units of grams and degrees Celsius, we get the value 79,200 joules. That's then the energy that has gone to the system. If we were after what is the heat flow from the surroundings, it would be negative 79,200 joules. The amount of energy that would be given off from the water to the surroundings if we went from the 100 degrees down to 24.3 degrees for this same quantity of water would be this negative 79,200 joules. So it depends on perspective in many ways. Here's another problem. 1.80 grams of ammonium chloride is dissolved in 10.0 grams of water, and the temperature drops from 21.8 degrees Celsius to 11.7 degrees Celsius. Calculate the heat of the reaction, so the heat of the dissolving of the ammonium chloride in the water, in units of kilojoules per mole. And we're given that the heat capacity of this solution is 4.18 joules per gram degrees Celsius. So we see the reaction that's occurring. It's the solid ammonium chloride dissolving in the water to form the separated ions, ammonium and chloride. And we're after the delta H of that process. So what we end up measuring is the surroundings. We measure the temperature, initial, final of the surroundings, the mass of the quantity of material involved, that would be the water and the ammonium chloride, and then we use that heat capacity. So it turns out we measure the quantities having to do with the surroundings. And then we use the equation Q of the system equals minus Q of the surroundings. And we're calling the surroundings in this case solution. So don't get mixed up. The surroundings are the solution. The system is the actual reaction, the dissolving process. So in this step 2, we are after the Q of the surroundings, the Q of the system. So that's equal to Sm delta T. So 4.18 joules per gram degrees Celsius times the total mass, 1.80 plus 10.0 grams, and then times the temperature change, final 11.7 minus initial 21.8 degrees Celsius. And we get the quantity negative 498 joules. Negative, well, because we're subtracting a bigger number from a smaller number, so we end up with a negative sign. Now, what that means for us is energy is transferred from the surroundings. That is, it takes energy to cause this dissolving to occur because it gets cooler. The system, the surroundings does. So it takes energy to cause that dissolving. The energy of the system has gone up. It goes up by the amount the surroundings goes down. So we have Q of the reaction, which is negative Q of the surroundings, negative Q of the solution. So that becomes then positive 498 joules. Or we could say delta H is positive 498 joules. Now, we were asked in the problem to find the delta H in units of kilojoules per mole. So what we have to do is convert these 1.80 grams of ammonium chloride into moles, divide that into our 498 joules, also convert from joules to kilojoules. And here we have done that. That's called here step 4. So 1.80 grams times the quantity 1 mole per 53.48 grams. That would be the molar mass of ammonium chloride. And that is 0.0337 moles. And so we divide our 498 by that quantity, and we also divide the 498 by 1,000 to convert from joules to kilojoules. So we end up with a value of 14.8 kilojoules per mole. We're working with Hess's law in this lab exercise as well. That's a way to determine the delta H of a reaction from a sequence of reactions, which when we manipulate those, they add up to the overall reaction. That is to say, if we have a reaction A plus B yielding C, and the delta H for that is delta H sub 1, and we have a reaction C forming D, and the delta H for that is delta H sub 2, and we add those two reactions together, we see that C is on the left side in one, the right side in the other. C cancels out, and our then overall reaction is A plus B yields D. And so the delta H of that overall reaction is the sum of those two delta H's, or delta H sub 1 plus delta H sub 2. So we apply that to this problem here, sample problem. So we're after the enthalpy change for the decomposition of hydrogen peroxide liquid, and that process is 2H2O2 liquid forming 2H2O liquid plus O2 gas. So we need to know what the delta H of that process is. And what we're given as data to work with is the reaction A and the reaction B. So in reaction A, we have H2 plus O2 forming H2O2. Delta H is negative 188 kilojoules. Reaction B is H2 plus 1/2 O2 forming H2O liquid. Delta H is negative 286 kilojoules. Now, what we do when we're working with Hess's law, if we have a reaction and we need to flip it, we need to change reactants and products, we're allowed to do that. When we do that, we have to change the sign of its corresponding delta H. When we multiply a reaction through by a term like a half or maybe 2, we then multiply the delta H, the corresponding delta H, by that 1/2 or that 2. Alrighty, so in reaction A, we have H2O2 formed, only one of them. Now, we want to flip that reaction around, so we're going to change the sign of the delta H. It's going to be positive 188. We also need to multiply through by 2, and then we will have 2 H2O2 on the left side as we need to, because that's what our overall reaction has. For the second reaction, it's got water in it. We need that. It's on the correct side, so that's good, but we do need to multiply it by 2. So we're going to multiply reaction through by 2, and we're going to multiply its delta H by 2. Alrighty, so we see that done over here. So we reversed reaction A, and we multiplied by 2. So you can see that reflected in the delta H of it, delta H sub A, it's now called. And in the second reaction, we had to multiply through by 2. So we do that for its delta H sub B. And we now are ready to add our two reactions together. So we see that we have 2H2 on opposite sides. We cancel that out. We have 2 O2s on the right side. We have 1 O2 on the left side. So we subtract an O2 from each side, so we end up with only 1 O2 on the right side. And when we add those reactions together, we get our overall reaction, the one we were after, 2H2O2 forming 2H2O plus O2. So now we have the delta H's, delta HA, delta HB all set up. All we do is the multiplying, the adding, subtracting, and we get the delta H for our reaction of interest to be negative 196 kilojoules. We also are working with enthalpies of formation, and for that we are using data in the appendix. And we are also using the equation, that summation equation. Delta H of the reaction is the sum over the moles, the stoichiometric coefficients, times the delta H of formation of the products minus the sum over n delta H of formation of reactants. The delta H sub F of products and reactants, we find those in the appendix. And those are particular to chemicals, which we find in the appendix in alphabetical order. N sub P, N sub R, those are basically stoichiometric coefficients found in our reaction. They are in units of moles. Okay, so we'll apply that to this reaction here. So we're working with the same reaction that we worked with above. 2H2O2 liquid forming 2H2O liquid plus, 2H2O2 liquid forming H2O liquid plus O2 gas. So we're after the delta H using this method. So we would look up the values for the delta H of formation of H2O2 liquid and find its value to be negative 188 kilojoules per mole. We would look up the value for H2O liquid. Be careful to distinguish between the phases. We find its value to be negative 286 kilojoules per mole. We would look up the value for oxygen and find its value to be 0 kilojoules per mole. So again, the negative 188, the negative 286, the 0, those are in the appendix. Alrighty, so now we apply our, let's go back to it for a moment, our summation equation, this one here. We're adding up everything of the products and subtracting the addition of everything of the reactants from that. Okay, so we do products minus reactants, so let's get our reaction shown. So we're looking at the product side first. So we have 2 for the 2 moles of water times its value, negative 286 kilojoules per mole, and then plus 1, because of the stoichiometric coefficient 1 for O2, times its value, which is 0. So that's all the products. So we do our, close our brackets there. And then we're subtracting that of the reactants. Well, we only have 1 reactant, but anyway, we have a 2 in front of the H2O2, so we have 2 times negative 188 kilojoules per mole. Notice that we have moles over moles, so moles cancels out. We have just units of kilojoules. Alrighty, so this simplifies to delta H of the reaction is 2 times negative 286 kilojoules minus 2 times negative 188 kilojoules. So just be careful about all those negatives. And we get negative 572 plus 376 kilojoules, or negative 196 kilojoules. So we got the same value as in the other method. We expect that. Sometimes they're a little different by a value, a number or two. All right, so you can skip the pre-activity and move into the report. And so in our first problem here, it's a little different than stuff we talked about in the intro above. We have a reaction, we have the delta H of it. So in this case, we're given the delta H. It's 90.7 kilojoules for the reaction as it's written. Based on the fact that it's positive, decide if the heat is absorbed or released. And then you calculate the amount of heat transferred in kilojoules when 1.60 grams of CH3OH are decomposed by this reaction. So what that delta H means is 90.7 kilojoules are given off, no, are required per mole of CH3OH. And so that is a conversion. So what you have to do is go from grams of CH3OH to moles of it. Then you can use the delta H as a conversion. Number 2 is similar to a problem that we talked about. So we're given the heat capacity of silver, we're given the heat capacity of water, we're given an amount of silver, an amount of water, and a temperature change, and we're asked how much energy is needed to heat silver, how much energy is needed to heat the same amount of water. The big difference has to do with their heat capacities. In number 3, that's similar to a problem we talked about in the intro. So we're given a dissolving reaction, we're given information about it, and we're going through it in a very similar way to what we went through in the introduction. And we're finding ultimately the enthalpy change in units of kilojoules per mole, much like we did in the problem above. Now we're using Hess's law, because we have an overall reaction whose delta H we're after, and we have this sequence of reactions. We have 3, so we just manipulate those. Remember, when you flip a reaction, you change the sign of its delta H. When you multiply through by a constant, you multiply its delta H by that same constant. Here's another one using Hess's law. Now we're doing the heats of formation, using the thermodynamic data, so be sure to use the data in the appendix. You should find that in Canvas for this lab activity. In this problem here, we are also using that heats of formation method, the thermodynamic data, But it's a little different than number 6 above. In number 6 above, we're after delta H of the reaction. In this one, we're given delta H of the reaction, and we're after the delta H sub F, the quantity that normally we find in an appendix. We're after that quantity for one of the reactants, the reactant ClF3. So write out your reaction, that summation equation. So put in everything you know. Put in all the 2's for the 2 moles and the 6 moles and the 1 moles. And then put in the delta H of the reaction, negative 1196. Put in the heats of formation that you find for the NH3, the N2, the HF, and the Cl2 in the appendix, and you will end up with only one unknown. You could call that X, and that will be the heat of formation of ClF3, and that is then what you are after. So when you are done with that, you are double check that you're happy with your work, scan it, PDF file, and then submit it.